Hello, good evening to all of you. So, welcome to the first lecture of thermodynamics here. So, this is specifically for the officer post of the HPCL here. Okay, now, and you already know the paper pattern and the type of question which can be asked, which we can analyze from the previous papers here. Okay, now. In this exam, you have to prepare for the theoretical knowledge as well as the numerical knowledge. So we are going to cover both the part here, and I will try to cover up the theoretical portion of the thermodynamics along with it. Okay, now. So before proceeding further here, please let me know, do you need the theoretical notes of the thermodynamics also? Please say it aloud, or you can also chat me on, text me on chat box here. Okay. Then I will share the PDF with you along with this question series here. Okay, now. So, few theoretical concept I will cover up in the today's class, and remaining I will share the notes with you. Okay. So let us start here. So first of all, just see in the thermodynamics what we have to cover. We have to know that the thermodynamics is a branch of science that deals with the study of energy interaction here. Okay, now it is dealing with the energy interaction here. Now, if we talk about the energy interaction is taking place between the system and between the surrounding. Now, coming back to the energy interaction, what kind of energy interaction can take place? So, generally, energy interaction simply means the property of the systems are changing. So, it can be energy interaction can take place in the form of work interaction. I can say it can take place in the form of heat interaction as well as in the form of I can say mass interaction. Okay, so generally there are three ways of energy interaction here, which we are going to see in the upcoming lecture. Now, coming back to the last interaction, mass interaction, it is not so much important for you, so you can skip that part. Only first and second portion is important for you, work interaction as well as the heat interaction. Okay, and there are some important formulas which you have to see. You have to just understand the type of processes which are taking place in the thermodynamics also. Okay, I hope you know the basic definition of the system and surrounding here. System is basically something which is under consideration, and anything which is on which our attention is focused is known as the system here. Coming back to the type of system, we already know that there are three type of system here. First one is open system, then we have a closed system, and then we have an isolated system. So there are three type of systems here. How do you classify these three type of systems here? These three type of systems are classified on the basis of these three type of interactions here. Okay, now on the basis of heat, work, and mass interaction, you classify the different type of systems here. For example, in the case of the open system, we have a work interaction, we have a heat interaction, we have a mass interaction. All the type of interaction is taking place in the open system. If we talk about the closed system, only the work and the heat interaction are taking place. There is no mass interaction taking place inside the system here. Okay, now? Okay, is it okay if I just continue in the English language? Or should I use Hindi?
अच्छा both यूज कर लो हिंदी और इंग्लिश
ठीक है. So now just see, in the case of an isolated system, there is no interaction of taking place between like heat, work and mass here. Okay, so isolated में किसी तरह का energy interaction आपको देखने को नहीं मिलेगा. In the case of closed system, you have a work and heat. In the case of open system, you have all the three type of energy interactions here. Now coming back to the surrounding here. Surrounding is something which is external to the system here. ओके तो जो भी आपके पास आप स्टडी नहीं कर रहे हो सिस्टम के अलावा जो भी कुछ है एनीथिंग एक्सेप्ट दिस सिस्टम इज गोइंग टू बी कंसिडर्ड एज अ सराउंडिंग. हाउ डू यू क्लासिफाई दिस हाउ डू यू डिफरेंशिएट दिस सिस्टम एंड सराउंडिंग? System and surrounding are differentiated on the basis of the, I can say, boundary here. Okay, now in this case, if we talk about the boundaries are of many types here. How many type of boundaries are there? Boundaries are of we have a moving body, we have a fixed boundary, we have a real boundary, we have a imaginary boundary. Okay, na? So generally there are four types here: moving, fixed, real, and imaginary one here. Okay, now so you can classify the boundary here on the different parts. Now coming back to the next thing, here in this case, if you just see, let us suppose if you have a piston cylinder arrangement here. Okay, and here we have a piston at number 1 position. Now what is happening? Piston is moving from 1 to 2. Piston is moving from 1 to 2 here. Now in this case, if you just see, a piston is basically considered as a movable boundary here. It is a movable boundary. Okay, it is a movable boundary here. Along with that, if you just see this particular portion which I'm highlighting here with a black color, it is a fixed boundary. तो ये आपके पास fixed boundary है सिलेंडर की जो आपके पास सरफेस है, and piston is going to be a movable boundary. Coming back to the real and imaginary boundary, let us suppose if you have a simple glass of water. एक सिंपल ग्लास ऑफ वाटर अगर आपके पास गिवन है, तो उस केस में अगर आप यहाँ पे देखोगे, वी में हैव अ वाटर. ओके, तो अब आपके पास जो रेड कलर का जो पोर्शन है, दिस रेड कलर सरफेस इज गोइंग टू बी कंसिडर्ड एज अ रियल बाउंड्री हियर. तो दिस इज द रियल बाउंड्री हियर. ओके, but if we talk about the top surface, this green color one, this is the imaginary boundary here. Okay, now so you have a fixed, movable, real, imaginary, and so on, this type of boundaries here. Coming back to the some important part here, whenever we are studying the thermodynamics, generally thermodynamics are of two types. Here we have a classical thermodynamics, here we have a statistical thermodynamics here. Okay, so from the name itself you can tell that which is a classical one and which is a statistical one. So here you can see in this case of statistical, we are dealing with the statics here. That simply means we are dealing with the data. Static का मतलब क्या होता है? Statistical data. आपके पास small number of data को हम deal कर रहे हैं. That means statistical thermodynamics is dealing with the microscopic behavior here. Microscopic here. तो जब आप माइक्रोस्कोपिक एनालिसिस कर रहे हो, दैट मींस वी आर डूइंग द स्टैटिस्टिकल थर्मोडायनामिक्स हियर. और जब आप यहाँ पे मैक्रोस्कोपिक एनालिसिस कर रहे हो, मैक्रोस्कोपिक एनालिसिस, दैट मींस वी आर डीलिंग विद द क्लासिकल थर्मोडायनामिक्स हियर. और अब आपके लिए कौन सी थर्मोडायनामिक्स इंपॉर्टेंट है? मैक्रोस्कोपिक. ओके, क्लासिकल थर्मोडायनामिक्स आपके लिए इंपॉर्टेंट यहाँ पे रहे, तो थोड़ा सा ध्यान रखना. नाउ कमिंग बैक टू द नेक्स्ट इंपॉर्टेंट पार्ट, we may have a different type of systems here. Oh, sorry, we may have a different type of properties here. So कुछ important terms है like what is the meaning of property, what is the meaning of state, you should know. अब आपके पास state का मतलब यहाँ पे, सॉरी, property का मतलब क्या होता है? Property का सिंपल सा मतलब है characteristics of the system. Characteristics of the system. और आपके पास यहाँ पे स्टेट की अगर हम बात करें, स्टेट क्या होती है? स्टेट इज द कंडीशन ऑफ द सिस्टम हियर. स्टेट इज द कंडीशन ऑफ द सिस्टम. मतलब क्या हुआ कहने का? जैसे मान लो अगर आपके पास एक सिंपल सा ग्लास ऑफ वाटर है, ग्लास ऑफ वाटर है आपके पास यहाँ पे, और अब आपके पास इस केस में कुछ वाटर रखा हुआ है जिसका प्रेशर, जिसका टेम्परेचर जो है वो 20 डिग्री सेल्सियस है. तो अगर मैं आपसे पूछूं कि आप आपके पास यहाँ पे टेम्परेचर क्या रिप्रेजेंट कर रहा है, तो टेम्परेचर इज रिप्रेजेंटिंग द कैरेक्टरिस्टिक्स ऑफ दिस वाटर. अब टेम्परेचर आपके पास यहाँ पे, जब कोई वाटर एक पर्टिकुलर टेम्परेचर को अटेन करेगा, when the temperature has been attained by the water, it is going to be, I can say, maintain a particular state here. So अभी आपके पास एक कौन सी स्टेट है? ये एक नॉर्मल स्टेट को रिप्रेजेंट कर रहा है. Now let us suppose if the temperature of 20 degrees Celsius is being changed to 80 degrees Celsius here. तो उस केस में क्या हुआ? Then the properties has been changed, characteristics has been changed. Along with that, when the 80 degrees Celsius is maintained, then the new condition is going to be attained here. अब क्या कंडीशन आपके पास यहाँ पे हो चुकी है? हॉट स्टेट आपके पास यहाँ पे हो चुकी है. ठीक है, ध्यान रखना. So we may say that the properties are acting as a coordinate. Properties are acting as a coordinate to define the state of the system here. मतलब क्या हुआ कहने का? अगर आपके पास एक सिंपल सा पिस्टन सिलेंडर अरेंजमेंट है एंड द पिस्टन इज एट पोजीशन नंबर 1. Okay, piston is at number 1 position, and I am saying that the pressure is 1 atmosphere. Let us suppose volume is, let us say, 1 meter cube. Okay, so if you just plot it on the pressure volume diagram, so pressure volume में कैसे plot करोगे? You are going to see the volume is 1 meter cube, and pressure is 1 atmosphere. So we may say that the state has been achieved. Which state? State number 1. So this state number 1 is basically is defined with the help of two coordinates, pressure and volume. Okay. So आपके पास properties क्या हुई यहाँ पर? properties are the coordinates to plot the state on the graph here. ठीक है ना, ये आप यहाँ पे ध्यान रखोगे. सेकेंड पॉइंट, इफ यू टॉक अबाउट द टाइप ऑफ प्रॉपर्टीज, प्रॉपर्टीज कितने टाइप की होगी आपके पास यहाँ पे? प्रॉपर्टीज आपके पास यहाँ पे दो टाइप्स की होती है. हियर वी हैव अ इंटेंसिव प्रॉपर्टी, इसको आप इंट्रिंसिक भी बोल सकते हो यहाँ पर. ठीक है. देन वी हैव अ एक्सटेंसिव प्रॉपर्टी विच इज अ एक्सट्रिंसिक वन. अब एक चीज का थोड़ा ध्यान रखना, even though intensive and intrinsic, I am saying that they are similar to each other, but there is a very small difference between these two. Okay. Intensive और intrinsic का मतलब यहाँ पे क्या हुआ? Those properties which are independent of the mass. We are going to see it later on that what kind of properties comes under the category of intensive and what type of property come under the category of extensive. If we talk about the extensive property, they are dependent on the mass here. Okay ना. अब इस केस में अगर आप यहाँ पे देखोगे, इंटेंसिव और इंट्रिंसिक के बीच में डिफरेंस क्या है? व्हाट इज द डिफरेंस बिटवीन द इंटेंसिव एंड इंट्रिंसिक हियर? Just give me a second. Just give me a second here. Just give me a second. Okay. चलो कोई नहीं. तो इन दैट केस इफ यू जस्ट सी, अब आपके पास यहाँ पे इंटेंसिव और इंट्रिंसिक के बीच में डिफरेंस क्या है? इंटेंसिव प्रॉपर्टीज आर दोस प्रॉपर्टी विच आर इंडिपेंडेंट ऑफ द मास. सिंपल से डेफिनेशन है. इंट्रिंसिक का मतलब यहाँ पे क्या हुआ? इंट्रिंसिक भी इंडिपेंडेंट ऑफ द मास होती है, बट दीज आर ऑल्सो इनहेरेंट टू द बॉडी हियर. These are also inherent to the बॉडी है. ठीक है ना. ये आपको यहाँ पे ध्यान रखना है. फॉर एग्जाम्पल अगर हम बात करें जैसे कलर की, किसी भी चीज का कलर जो है बेसिकली वो इंटेंसिव है. ओके. बट इट इज नॉट अ एक्सट्रिंसिक हियर. कलर क्या है बेसिकली? कलर आपके पास इंटेंसिव हुआ बिकॉज इट इज नॉट डिपेंडिंग अपॉन द मास ऑफ द सिस्टम. बट if I change the chemical composition here, the corresponding color of the system is going to change at a constant mass here. So I can say it is not an intrinsic parameter. So there is a very small difference between the intensive and intrinsic, even though they can be used interchangeably here. Okay. Any doubt? Yes. If you have any doubt, please let me know. Okay. Now coming back to the first question here. Consider the following statement about an isolated system. No heat is being transferred, no work is done, no fast mass flow across the boundary of the system, no chemical reaction take place within the system here. So that is a simple case. In the case of an isolated system, no mass, no work, no heat can be transferred here. Okay. But there may be a chance that chemical reaction may take place here. Why? Because if you just see, the perfect example of isolated system is a universe here. Everything comes under the category of universe. Okay. So there may be a chance that inside the universe, the changes may take place. Any type of changes may take place. But from the outside to the, from the surrounding to the system, there is no mass, heat and work interaction there. Okay, na? Next part. So option number C will be the correct answer here. Consider the following property: energy, entropy, Gibbs energy, volume, and so on. Which of the following are the intensive properties here? Yes. Now we are again moving toward the intensive property, that is independent of the mass. Independent of the mass here. Now in this case, we will just see the pressure, temperature, viscosity, and elasticity. These are the four properties which are completely independent of the mass. No matter if you change the mass of the system, these pressure, temperature, viscosity are not going to be changed here. Okay. Because they are the characteristics of the system. But if we talk about the energy, entropy, Gibbs energy, and volume, they may change due to the amount of matter in it. If the amount of matter is changing, the corresponding properties are going to be changed here. So option number B is going to be the correct answer here. All of these first four are going to be considered as an extensive property. Okay. Next part. Absolute zero temperature is taken as. Okay. Now just see the information related to the absolute zero temperature first. What is the meaning of temperature here? Temperature basically tells you about the degree of hotness and degree of coldness here. Degree of hotness and coldness. The measurement of temperature inside in the thermodynamics is a very, very important part here. Okay. For that purpose, what we study the zeroth law of thermodynamics. Zeroth law of thermodynamics. So the statement of the zeroth law of thermodynamics is very, very simple. It simply states that if the temperature of A is equal to temperature of B and temperature of B is equal to temperature of C, therefore I can say then A and C are going to be same if they are not making a contact with each other. So here we have body number A, which is making a contact with a body number B, and B is also making a contact with a body number C. Then individually A and C temperature are going to be same. Okay, that's a simple statement. Now we say that the zeroth law of thermodynamics forms the basis of the temperature measurement. Forms basis of the temperature measurement here. Why do we say that it forms the basis of a temperature measurement? Because the zeroth law of thermodynamics gives the concept of a thermal equilibrium here. Thermal equilibrium here. Okay, and to maintain the and to calculate the temperature here, to measure the temperature here, the required condition is that thermal equilibrium is properly maintained between the system and surrounding here. Okay, that is a required condition. Now coming back to the next part, absolute zero temperature. See that it is not possible to attain the absolute zero temperature in the real scenario. That is the third law of thermodynamics, that it is impossible to attain the absolute zero temperature. Okay. Now, in order to measure the temperature, we may have a different temperature scale. So there we study two type of temperature scale. First one is a temperature scale, and the second statement is the thermodynamic temperature scale. Thermodynamic temperature scale. Now, what is the meaning of temperature scale? Temperature scales are those scales which are used to measure the temperature. Okay, it is used to measure the temperature. Now, what is the meaning of thermodynamic temperature scale? Thermodynamic temperature scale are also used to measure the temperature. But along with that, uh, it also defines the 0 Kelvin temperature. Or I can say you are going to get the absolute zero value of the temperature in the thermodynamic temperature scale. It also defines the 0 Kelvin of the temperature. Now just see, in order to define the temperature, we may have a different type of scale. Like we have a degree Celsius scale, we have a degree Fahrenheit scale, degree Rankine scale. Okay, we have a degree Kelvin scale. So there may are different type of scales here. In general, if you just see, you can also develop your own scale to measure the temperature. Okay, and it may have a arbitrary values also. Okay, remember that condition. Now, in this case, if you just see, if you talk about the thermodynamic scale, temperature scale, only the Kelvin scale is there. Kelvin scale is there, which is considered as a thermodynamic temperature scale. Why? Because it defines the absolute zero temperature of the absolute zero temperature here. And what is the value of the absolute zero temperature? The absolute zero temperature is defined as minus 273.15 degrees Celsius here. So that is the value of the absolute zero temperature, or option number C is going to be the correct answer. So that is again a very simple case. Okay, should I give you? Okay, so just see, in order to measure the temperature, we may have a different type of thermometers also. Okay, so now just see the concept of a type of thermometer. in order to measure the different type of in order to measure the temperature here, we may have a different type of thermometers. Like we have an idle gas thermometer, here. Then we have a mercury in glass thermometer, which we use in a normal day-to-day life. Mercury in glass thermometer. Then we may have, I can say, thermocouple. Then we have resistance-based thermometer. Okay. So idle gas thermometer हो गया. We have a mercury in glass thermometer, thermocouple, resistance-based thermometer here, and there is one more thermometer which is basically work on the principle of a Seebeck effect here. Sorry, Peltier effect here. I am not remembering the name. Thermocouple, resistance-based thermometer. Yes, resistance is based working on a Wheatstone base. Thermocouple is basically a EMF here. No, that's it. Now, in this case, the idle gas thermometer are of further two types. Here we have a constant pressure thermometer, and then we have a constant volume thermometer. Now, in all of these thermometer here, what do we have? We have a defined thermometric property. In each thermometer, we may have an individual thermometric property. What is the meaning of thermometric property here? Thermometric property means the property with the help of which we are measuring the temperature. We are measuring the temperature here. For example, if you just see, in the case of an idle gas thermometer, we are using the idle gas equation. Okay, so there we have a constant pressure, constant volume thermometer. In the case of a constant volume thermometer, by measuring the change in volume, we are measuring the change in temperature. So volume is acting as a thermometric property. In the constant volume thermometer, by measuring the change in pressure, we are measuring the change in temperature here. So that means in the case of constant volume, pressure is acting as a thermometric property. In the case of a mercury in glass thermometer, how do we measure the temperature? By measuring the length here. Okay, how much mercury has been, by how much length the mercury has been expanded. With the help of it, we measure the temperature. In the case of thermocouple, the EMF is being induced. Okay, so by calculating how much EMF has been induced, we calculate the temperature here. So EMF is the thermometric property. In the case of resistance-based thermometer, by calculating how much resistance has been changed, we are defining the temperature. So we may say the resistance is acting as a thermometric property. Okay, so there are different ways to measure the different temperatures. Now just see one more thing. I have told you that we may define our own temperature scale. Okay, we have seen that we have a Kelvin scale, we have a degree Celsius scale, we have a Fahrenheit scale, we have a Rankine scale, and it is not like that there are only 4 scales. You can also define your own temperature scale, which can help you to measure the temperature there. Okay, na? Remember that part. Now, in this case, if we just see, in the case of thermocouple, what is happening? Here we have a 2-wire. Here we have 2-wire which are made up of dissimilar metals here. There it is a wire number A, and there we have a wire number B. Okay, both of them are in contact with each other from their end. Now what is happening? Now what we are doing, we are maintaining the one end of the these 2 wires at a temperature of TA, and we are maintaining the second end of the joint at a different temperature, let us say TB. Now what is happening? Due to the temperature difference, there is a EMF induced in it. There is a EMF induced in it. Okay, now in this case, if you just see how much EMF has been induced, by calculating the EMF induced, we are calculating the change in temperature. Okay, that is how the simple thermocouple works here. Understood? So this is also known as the Seebeck effect here. Remember that part. So we say the thermocouple works on the Seebeck effect here. Understood? Any problem? Yes, tell me your doubts now. So here we have a different type of variation, or I can say the different type of relationships between the thermometric property and the temperature. For example, in the case of Seebeck effect, I have told you that we are going to have EMF induced here. Okay, larger the temperature difference, larger will be the EMF induced. Smaller the temperature difference, smaller will be the EMF induced. Now, the EMF and the temperature relation can be defined in different. For example, I can define the relation in this form. Okay. I can define the relation in this form A plus BT. So here you can see the EMF and the temperature may vary cubically, may vary linearly, or it may vary parabolically here. Okay. It depends upon the accuracy. It depends upon the accuracy here. And if we talk about the resistance-based thermometer, resistance-based thermometer work on the principle of a Wheatstone bridge. Wheatstone bridge principle here. Okay, remember this thing. Now, coming back to the next part, you have to remember that for the different temperature range, which type of thermometers are basically used. Okay, that is very important for you. For example, if we just see, if you have a temperature ranges. Okay, so first of all, just define, here we have different point. Like first we have a oxygen point. What is the meaning of oxygen point? Oxygen point means the normal boiling point of the oxygen. Normal boiling point of the oxygen. Okay, boiling point of the oxygen is around minus 183.3 degrees Celsius. Just remember the value. Okay, then we have a, I can say, ice point. We have a ice point which is having a value of 0 degrees Celsius. Then we have a triple point. Which is having a value of, which is having a temperature corresponding to 0.01 degrees Celsius. Then we have a steam point which is having a value of around 100 degrees Celsius. Then we have a, I can say, a sulfur point. Which is having a value of 444.4 degrees Celsius. Okay, and then we have a gold point, which is basically a normal melting point of the gold. Normal melting point of the gold. Okay, which is equal to 1063 degrees Celsius. Now you may ask, sir, why we are studying these temperatures here? What is the need? I have told you that we may have defined the different type of temperature scales. It is not like that we have degree Celsius, degree Fahrenheit, degree Fahrenheit only. We may have all the different type of scale. आप कोई भी temperature scale अपनी need के according define कर सकते हो. Okay, and in order to define the different type of temperature scale, you have to do the calibration. Okay, so calibration करने के लिए required है कि आपके पास कोई criteria हो. Certain criteria should be there. Okay, so we may use different points to calibrate the different type of scale. तो ऑक्सीजन पॉइंट का आप यूज कर सकते हो, आइस पॉइंट का आप यूज कर सकते हो, ट्रिपल पॉइंट का आप यूज कर सकते हो, स्टीम पॉइंट का आप यूज कर सकते हो. ठीक है, कोई भी दो टेम्परेचर्स का आप यूज कर सकते हो कैलिब्रेशन पर्पस. नाउ इंपॉर्टेंट थिंग, नाउ द इंपॉर्टेंट पार्ट इज, let us suppose if you have a temperature ranges from minus 183 degrees Celsius to 0 degrees Celsius. ऑक्सीजन पॉइंट से लेके आइस पॉइंट तक अगर आपके पास टेम्परेचर रेंज है तो आप कौन सा थर्मोमीटर यूज करोगे? तो इन दैट केस यू यूज द रेजिस्टेंस बेस्ड थर्मोमीटर हियर. ठीक है, ध्यान रखना, आप रेजिस्टेंस बेस्ड थर्मोमीटर आप यूज यहाँ पे करते हो, जिसके अंदर हम प्लेटिनम वायर का यूज यहाँ पर करते हैं. प्लेटिनम वायर का आप यहाँ पे यूज करते हो. अगर आपके पास टेम्परेचर रेंज जो है वो 0 डिग्री से स्टार्ट हो रही है, 0 डिग्री सेल्सियस से 660 डिग्री सेल्सियस तक यूज हो रहा है. In that case also you are using the resistance based thermometer. Resistance based thermometer. Okay. In that case, if you just see the wire which we are using is a, oh sorry, आपके पास यहाँ पे अगर हम बात करें, अच्छा जस्ट गिव मी अ सेकंड, दोनों में ही आप पास प्लेटिनम वायर का यूज कर रहे हो ना, ठीक है, दोनों में ही आप यहाँ पे प्लेटिनम वायर का ही यूज करते हो, नो वरी. ठीक है. अगर आपके पास यहाँ पे टेम्परेचर रेंज जो है वो हमारे पास 660 से 660 डिग्री सेल्सियस से 1063 डिग्री सेल्सियस तक लाई करता है. इन दैट केस आपके पास कौन सा थर्मोमीटर हम यूज करेंगे, देन यू यूज द थर्मोकपल हियर. ध्यान रखना ये पूछा जाता है आपके पास यहाँ पे कि टेम्परेचर रेंज के लिए कौन सा थर्मोमीटर यूज करोगे, तो इस टेम्परेचर रेंज के लिए थर्मोकपल का यहाँ पे यूज करते हो. ठीक है. Oh, sorry. You have to remember that for which temperature range you have to use this thermometer here. Okay. So if you are using a thermocouple, the temperature range should be 660 degrees Celsius to 1063 degrees Celsius here. Okay. Now, so just remember the temperature range, along with that the name of thermometers here. And if the temperature is more than 1063 degrees Celsius, then you have to use the pyrometer here. Okay. In one PSU exam, they have asked you that what is the range of thermocouple here, and they have provided the range up to 1500 degrees Celsius here. So in general, the temperature range lies up to 1500 degrees Celsius here. Understood? Any doubt? So if you have any doubt, please let me know. Now tell me your doubts. Okay. Now let us move toward the next part. So do we have you seen the question here? Yes. Next part is a series of operations which take place in a certain order and restore the initial condition at the end is known as reversible, irreversible thermodynamic cycle. Now, what is the meaning of that? I have already told you first. It is for thermocouple here. Thermocouple can be maximum. It can be used up to 50 degrees Celsius here, but in practical scenario, we use it between the between the sulfur point and between the gold point only. Okay, no? Next, here we have studied that the meaning of property. We have seen that the properties are defining the characteristics of the system. Then we have seen that the state is representing the condition of the system here. Condition of system here. Characteristics of the system and the condition of system here. Now, what we are going to do here, we have also seen that properties are basically acting as a coordinate to define the state or to fix the state here. So let us suppose if you have a graph here, then what I am doing, I am fixing a state here. I am fixing a state number 1 with the help of a properties P1 and V1 here. Let us suppose it is a graph between the pressure and volume. Okay. Now what is happening? So this is a case when the piston cylinder in the piston cylinder arrangement, piston is at number 1 position. Now what is happening? Now the piston is moving from 1 to 2. So as the piston is moving from 1 to 2, the corresponding pressure is decreasing and volume is increasing here. After that, we have attained some another state here. Okay. So you can see here we have initial state 1, then we have initial state 2. And if you just know the in between states here, you may define a path here. Okay. So here we have defined a path. So this is our path. So path is basically telling you, or I can say path is representing the series of change of state when you are moving from initial state 1 to final state 2 here. Okay. Now, when a path is properly defined, when the path is properly defined, then we say that then it forms a particular process here. And in thermodynamics, generally, we studied 5 type of processes here. What are the 5 type of processes? The first one is the constant volume process, constant pressure, constant volume, constant temperature, then we have a adiabatic process, and then we have a polytropic process. So these are the 4-5 processes which we see while moving from initial state to final state. Now let us suppose, if you are moving from initial state 1 to another state 2, and then 2 to 3, and 3 to 4, and 4 to 5, and then again moving back again to 1 here. So if the number of processes are carried out in such a way that initial and final state are same, then we say it forms a thermodynamic cycle here. Now, what is the meaning of cycle? Cycle is basically representing you the number of processes carried out in such a way that initial and final point are same. Understood? So that is known as a thermodynamic cycle here. Now, there may be a chance that in the thermodynamic cycle, any one process may be reversible in nature, or any one process can be act as a irreversible process here. Now, coming back to the next part, what is the meaning of quasi-static process here? What is the meaning of quasi-static process? Now let us suppose if you have a piston cylinder arrangement, like in this way, the piston is at number 1 position, okay, and you know that inside condition the pressure is P1 and the volume is V1. Okay, so now what I can do, I can simply define this particular state in a pressure volume diagram. So it is being represented by point number 1. So here we have volume 1, and then we have a pressure P1 here. Now let us suppose, now what is happening? You are moving from 1 to 2. You are moving from 1 to 2. Okay. And at point number 2, you have a pressure P2 and volume V2. So which is being represented here. Which is being represented here. P2, V2 here. Now the question is, how you are moving from 1 to 2? In which way you are moving from 1 to 2 here? Now let us suppose if I put a weight of 100 kg, if I put a weight of 100 kg on the piston at once, then what will happen? The piston will suddenly move from 1 to 2 here. Okay. Now tell me, if the weight is suddenly put over the piston, and when the piston is moving from 1 to 2, then at point number 3, let us say you are getting the pressure of, P3 and you are getting the volume of V3 here. Okay, what I am trying to say, you are putting a 100 kg of weight at once over the piston, and the piston is moving from 1 to 2. Now, when the piston has reached point number 3, at that point of time, the pressure is P3 and volume is V3. Now, let us suppose, so now where is the piston? The piston is at number 2 here. Now, what you are doing? Now you are removing the weight here. Now, let us say you are removing the 100 kg weight. Then what will happen? The piston will again move back from 2 to 1 here. As you remove the total weight, the piston will move from 2 to 1. Now tell me, at the same position, at the same position 3, are you going to get the same pressure or volume, or are you going to get the different pressure value? Just tell me that. Yes, tell me. Are you going to get the same value of the pressure at point number 3 when the piston is moving suddenly from 2 to 1 here, or are you going to get a different value? Yes, give me some response here. Different. That means when the piston is moving from 1 to 2, you are getting the value of P3, but when you are moving from 2 to 1, at the same point you are getting the different value. That simply means the properties are not going to have same value at the same point. Okay, why so? Because the piston is having a sudden movement here. Okay, the piston is having a sudden movement. Now let us suppose Instead of moving suddenly, now what you are doing, instead of putting the entire weight at once, what you are doing, you are putting a small amount of weight here. You are putting a small amount of weight in an increment of 0.01 kg here, let us say. Okay, now the weight is incrementing from 0.01 kg to 100 kg here. Then what will happen? The piston will slowly move from 1 to 2. Okay, and at each movement you are going to get a defined value of pressure and volume. Now what is happening? The piston is moving slowly in from 1 to 2 as you are putting a weight of 0.01 kg in the incremental form. Okay, and you are going to get that we are getting the some equilibrium values at each and every state here. Okay, so in this way you are moving from 1 to 2. Now let us suppose again I am asking you that, oh sorry, again I am asking you that at position number 3, the pressure is P3 here. The pressure is P3 and volume is V3 here. Can I say that if you remove the small amount of weight, small amount of weight of 0.01 kg, the piston will again move back from 2 to 1 here. And you are going to get the same pressure and volume value at point number 3, which you are getting in the forward path. Yes or no? Yes. So we can say it can be considered as a reversible process. So first of all, what is the meaning of quasi-static process? First of all, the quasi-static process has the characteristics of the infinitely slowness here. It is having a characteristics of infinite slowness here. Okay, that is the first thing. Second thing, if you are getting the same equilibrium states while moving from 1 to 2 position or 2 to 1 position, then we may say the quasi-static process is going to be considered as a reversible process here. So I can say the quasi-static process can be considered as a reversible process here, but the required condition is you have to avoid the friction in this case. Neglecting friction. So let us suppose if the friction is being considered, in that case the quasi-static process is going to be considered as an irreversible process. So irreversible process simply means that you are not getting the same properties here. Okay, so there is a difference between the quasi-static process, reversible process, and irreversible process here. So quasi-static is a reversible process without friction. Quasi-static is a irreversible process considering the friction here. Okay, remember that. Next part. Yes. Which thermometer is independent of the substance or the material used in its construction here? So now just see. Here we have an ideal gas thermometer here. Ideal gas thermometer are basically the those thermometer which are independent of the substance. Why so? Because here we don't consider the which type of here we don't, it doesn't matter which type of fluid you are using here. Why? Because ideal gas thermometer, if we talk about, there are of two types: constant pressure thermometer and constant volume thermometer. In the case of a constant pressure thermometer, we have a volume as a thermometric property. If we talk about the constant volume here, pressure is basically considered as a thermometric property. Okay. Now, next thing, both of these thermometer basically works on the ideal gas equation, which is written as PV equal to MRT. Now just read about what is the meaning of ideal gas equation. That is very important for you. Just see. First of all, ideal gas equation, which is also known as the perfect gas equation. Perfect gas equation. It is written as PV equal to MRT. What is P? P is representing the absolute pressure here. absolute pressure. V is representing the total volume here. Okay. M is representing the mass of the system here. R is representing the characteristic gas constant here. ठीक है. And T is representing the absolute temperature here. Now, absolute pressure has a unit of Pascal. Volume is having a unit of meter cube. Mass is having a unit of kilogram. Characteristic gas constant is having a unit of joule per kg Kelvin. Absolute temperature is having a unit of Kelvin here. Okay. Now, we may have a different values. We may have a different values of the characteristic gas constant for different gases. Remember that part. That is very important. Now, PV equal to MRT is written in the form of per unit mass. In the form of, sorry, it is represented in terms of mass of the system. In terms of mass here. Okay, in terms of mass, or I can say in terms of kg here. It is represented. Now, coming back to the second form, here we can also rewrite this equation in the form of PV equal to nR bar T. P, V, and T are same. Absolute pressure, total volume, absolute temperature. What is N? N is representing the number of mole here. Number of mole, which is represented in the form of mole only. R bar is representing the universal gas constant here. Okay, which is represented, which is having a unit of joule per mole Kelvin here. Joule per mole Kelvin here. Okay. Remember that this equation is written in the form in terms of number of moles here. Can anybody tell me what is the meaning of mole? What is the meaning of 1 mole of a substance? Yes, tell me. Mass per unit molar mass. Okay, that is a mathematical formula. What does it represent? What does it represent here? Just tell me. Avogadro number. Yeah, that is also correct here. Total number of molecule present in a given mass. Okay. Now just see what is the meaning of mole here. Let us suppose if you have a 1 mole of oxygen. If you have 1 mole of oxygen, let us suppose if you have 1 mole of CO2 here. 1 mole of O2 represent that it is consisting of 32 grams of oxygen here. 1 mole of CO2 represent that we have a 42 gram of CO2 here. That means the mole is representing the mass only, but here 1 mole consists of a mass equivalent to the molecular weight of a substance here. Okay, now what is the relationship between the mole and a mass? 1 mole consists of the mass equivalent to the molecular weight of a substance. Okay, so if somebody asks you that what is the meaning of 1 mole of atmospheric air. 1 mole of air consists of 29 gram of air. Okay. If I assume 29 as a molecular weight. Now, what is the meaning of Avogadro number, which some student has tell? Actually, 1 mole of any substance consists of how many number of molecules? It is equivalent to 6.022 into 10 to the power 23 number of molecules here, which is equivalent to the Avogadro number. Okay, remember that. So each substance consists of same number of molecules when it is present equal to 1 mole of a substance. So 1 mole unit is basically used in the chemistry. 1 gram, kilogram is basically used for our daily day-to-day life here for calculating the number of matter. So the amount of matter here. Okay. Any doubt? Please tell me if you have any doubt here till now, because I have to tell you the third form of the ideal gas equation. And also remember, there is a certain relationship between the characteristic gas constant and the universal gas constant. The universal gas constant is equivalent to the molecular weight multiplied by the characteristic gas constant here. So let us suppose if you want to calculate the characteristic gas constant of the oxygen, it is equivalent to R bar upon molecular weight of oxygen. Okay, 8.314 divided by 32 here. If you want to calculate the value of R of air, it is equivalent to 8.314 divided by 29, which is equivalent to 0.287 here. Okay, in this way you can calculate the characteristic gas constant. Now just see the next important part. We have represented the ideal gas equation in terms of mass, in terms of number of moles here. Now we are going to represent the characteristic ideal gas equation in terms of number of molecules. So here we know that 1 mole of any substance, 1 mole of any substance consists of how many number of molecules here? Can I say that? The Avogadro number of molecules here. A is representing the Avogadro number of molecules here. Okay, now A is the Avogadro number. So let us suppose if you have n mole of a substance, n mole of any substance here. So total how many number of molecules are going to be there? Can I say that n into A will be the total number of molecules? Yes or no? Just tell me. N multiplied by A will be the total number of molecules in the n mole of any substance. Okay. Let capital N equal to N into A. Let capital N is representing the total number of molecules. N is the total number of molecules. Total number of molecules in n number of substances, n number of moles here. Yes, tell me everything is clear now? If you have any doubt, please let me know till now. Okay, so now just see. Now we know that PV is equal to NR bar T. Here we know that. Okay, so what I am doing, I am writing the number of moles in the form of capital N upon capital A. Okay, from here you can see multiply by R bar T, which can further be written as PV equal to capital N R bar upon Avogadro number into T. Okay, so further the ideal gas equation can be written as PV equal to N into K into T. So this is the third form of writing the ideal gas equation or a perfect gas equation here, PV equal to NKT, where K is representing the Boltzmann constant. Boltzmann constant, which is having a formula of characteristic gas constant, universal gas constant divided by Avogadro number. Okay, and along with that, you can see this is representing the equation in terms of number of molecules here. In terms of number of molecules here. Okay, so there are three ways of writing the ideal gas equation: PV equal to MRT, PV equal to NR bar T, PV equal to capital N, K into T. That you have to remember. Next part. A new temperature scale in degree N is to be defined. The boiling and freezing point on this scale are 400 degree N and 100 degree N respectively. What will be the reading on the new scale corresponding to 60 degrees Celsius? So here we have defined a new scale. First of all, in our old scale, that is degree Celsius scale, in the degree Celsius scale, here we have 100 degrees Celsius temperature. Here we have 0 degrees Celsius temperature. Okay. Now in this case, if you just see, we have defined a new temperature scale, which is the degree N. Now 100 degrees Celsius is represented by 400 degree N in the new scale, and 0 degree Celsius is represented with the 100 degree N in the new scale. Now, what do you want to calculate? So you are measuring a body which is maintained at a temperature of 60 degrees Celsius. Now you want to find out that what will be the value of that body, what will be the temperature of that body in the new degree scale. So here we have 60 degrees Celsius. Then what is the value of this here? We have to find out. Okay. Now, first of all, if you just see, uh, here we have to write down the equation of line. Equation of line here. Okay. So equation of line you can write in any form. Either you can write in this form 60 minus 0 degrees Celsius, 60 degrees Celsius minus 0 degrees Celsius divided by 100 degrees Celsius minus 0 degrees Celsius. Okay. Or either you can write 100 minus 600 degrees Celsius minus 60 degrees Celsius divided by 60 degrees Celsius minus 0 degrees Celsius. It's all up to you. You can write in any form. Corresponding to 60 degrees Celsius, we don't know the temperature. Let us suppose it is x degree N. So I'm writing x degree N. Corresponding to 0 degrees Celsius, we are having a value of 100 degree N. Corresponding to 100 degrees Celsius, we are having a value of 400 degree N. And corresponding to 0, we have a value of 100 degree N. So if you just solve it, you are going to get the value of x in the new temperature scale. Okay. So if you calculate it, you are going to get the value as 2, 5, 5 to 6, 30, 80. You are going to get the value as 280 degree N here. Okay. In the same case, if I write down in the second form, corresponding to 100 degrees Celsius, we are having a value of 400 degree N. Okay, just give me a second. Let me see. You have to write down the equation of line, and that's it. Okay. So you know all the temperatures in the degree Celsius scale. So I'm writing the random values. Let us suppose I am writing 60 degrees Celsius minus 0 degrees Celsius divided by 100 degrees Celsius minus 0 degrees Celsius. I have written the expression in this form. Now, corresponding to 60 degrees Celsius, we don't know the value. The temperature is unknown. So we have written x. Corresponding to 0, we have a value of 100. Corresponding to 100 degrees Celsius, we are having a value of 400. And again, corresponding to 0 degrees Celsius, we are having a value of 100. Okay. So on the left hand side, we are writing the expression in the degree Celsius. On the right hand side, we are representing the relation in the form of degree and scale. Understood? Now tell me if you have any doubt. So if you just solve it, you are going to get 60 by 100 is equal to x minus 100 divided by 300 here. And if you just solve it, you are going to get the value of 280 degree N. So that simply means if the body is representing a temperature of 60 degrees Celsius, in the new temperature scale, you are going to get the value of 280 degree. Now similarly, let us suppose if some student write down the expression in this form 100 minus 60, 100 degrees Celsius minus 60 degrees Celsius divided by 60 degrees Celsius minus 0 degrees Celsius. Now you can see corresponding to 100, we are having a value of 400 degree N. Corresponding to 60, we are having a value of x degree N. Corresponding to 60 again, x again, 0, 100 degree N. Okay. So if you just solve it again, you are going to get the same value only. You are not going to get different value. Okay. The value will come out to be same, 280 only. Just try to solve it and get your answer here. Any doubt? So that's a very simple case. Okay, so that is how you define the different temperature scales in the thermodynamics. Now tell me if you find out any problem here. Okay. Now just see. A spring-loaded piston cylinder device contained 1 kg of CO2 initially at 100 kilopascal here at 25 degrees Celsius. Now heat is transferred to CO2 causing the, okay, I will cover that part in the tomorrow's class here because we haven't covered it right now. Okay. This question we have already seen. Work done, we haven't covered it right now. Okay. Now let's move toward the topic question number 10, that is a system will be in thermodynamic equilibrium. Now what is the meaning of that? In today's class, I am going to cover only the theoretical portion here. From tomorrow, we are going to see the numericals. In this question, we have to mark a system will be in thermodynamic equilibrium if it is in mechanical, chemical, thermal here. Okay. Now what is the meaning of thermodynamic equilibrium? Let's see. The answer is correct. All the three conditions has to be satisfied. Okay. If three conditions are satisfied, then we say the body is going to be in thermodynamic equilibrium. Now, what is a required condition? What is a required condition? First, all of these three type of equilibrium has to be met. Okay. Whenever we say that the body is in thermodynamic equilibrium with the surrounding, that simply means the body is also in dead state with the surrounding here. Why? Because a system is in thermodynamic equilibrium simply means that it does not have any capacity to do the energy transfer with the surrounding here. Okay, remember that. So I can say body is in thermodynamic equilibrium and a body is in dead state. Both are the same thing. That simply means there is no energy left inside the system which can be extracted from it. Okay, remember that part. So that is a required condition for a body to be in thermodynamic equilibrium. Can anybody give me some practical example? Can you tell me some practical example where the thermodynamic equilibrium has been established between the system and surrounding? Just tell me. Hmm. Yes. If you just see, let us suppose if you just put a glass of tea, a hot cup of tea for a very long period of time on a table. Okay. If a body is kept for a very infinitely long period of time here or a very sufficient long period of time, then we may say that the mechanical equilibrium, thermal equilibrium, and all the chemical potential is going to be diminished. That is, chemical equilibrium is going to be established here. So I can say that time is going to be create a very important effect to maintain the thermodynamic equilibrium between the system and surrounding here. Okay, now. Next part, the specific heat ratio K is given by the expression. Okay. So now what is the meaning of, okay, so we haven't covered up the specific heat word here now. So let's just see what is the meaning of specific heat. Specific heat simply representing you the amount of heat which is basically required to raise the temperature by 1 degree Celsius of a unit amount of a mass here. Okay. So here we have different values of specific heat. Here we have different values of the amount of heat under the constant pressure condition and under the constant volume condition. Okay. We will cover that part in more detail once we cover up the first law of thermodynamics here. So just right now, just remember that we have seen a one concept, characteristic gas constant. Characteristic gas constant is nothing but it is equivalent to the Cp minus Cv here. Okay, and there's one more term that which is known as the adiabatic index, which is defined as the ratio of Cp by Cv here. Okay. Now, what we have to find out? We have to find out the specific heat ratio. Specific heat ratio simply means we have to find out the value of the gamma here. Okay, so now you can see first Cp is representing the gamma times Cv here. Okay, from the equation number second, and we may say R is going to be equivalent to gamma times Cv minus Cv. After further simplification, we can say gamma times Cv is equal to R plus Cv here. And after simplification, we are going to see 1 plus R upon Cv here. That means the gamma is equivalent to 1 plus R upon Cv here. Okay. So option number C is going to be the correct answer. And also remember some of the important data. You have to remember the data for the air. For air, you have to remember that the value of the Cp is around 1.005, Cv is around 0.718, the value of gamma is around 1.4, the value of the characteristic gas constant is 0.287 here. Okay. For water, you have to remember the value of Cp and the value of Cv are same, which is equivalent to 4.18. For ice, you have to remember the value of Cp and value of Cv is same, which is equivalent to 2.09. Okay, all these three results you have to remember. Now tell me any doubt. Okay. So now just see, that's it for today's class here. Now tell me, okay, now the remaining thing which we are going to see in tomorrow's lecture here. Okay, and tomorrow we are going to see some basics concept again, and we are going to also see the expression of work done, heat transfer, and the first law of thermodynamics also. Okay, and the remaining questions which I have left today, the numerical questions, we will cover in the tomorrow's part here. Do you have any doubt? Yes, confirm me once. Abhishek, you don't have to make the notes here. I am going to share the notes with you. Don't worry. Sonu, first of all, just see. I think the Rajesh sir has also done the previous year paper analysis of this particular exam here. So there you must see how many marks has been asked from this particular thermal engineering part here. Have you seen the previous year paper analysis video by Rajiv sir, or maybe I think Vijendra sir have done here? Just check it once on the YouTube here. Okay, now there you will get an idea how many questions can be asked from this particular topic, from this particular subject here. Okay. Okay, so that's it for today's class here. Now the remaining things we are going to see in the tomorrow's class here. Okay, now. And if you don't get the video here, please let me know. I will make you sure that the video will be shared with you. Okay, in your group itself. Don't worry. Okay. So I'm closing this session now. Now we will meet tomorrow at the same time.